Hey folks, it's Federico here, and today we're going to see how we can create this algorithm called circle packing in Max using shaders, so using the GPU, using transfer feedback shader for the actual algorithm, and a render shader to transform the vertices of the GGL mesh into circles. But first of all, what is actually circle packing? Where is this algorithm where we have a bunch of points in random positions, and they start to grow until they touch the edge of another circle, and then they stop growing. So this is actually a perfect algorithm to put on the GPU using transform feedback, because we need to know the previous size of the circle to compare it with the sizes of the other circles, and then we can apply this effect to images, for example. So let's get a bit more circles, 20,000 circles. So that's pretty cool. In this tutorial we are not going to see how to create this image part, we are going to see how to create the basic algorithm, which you can then use for all the effects you want, like applying it to images or videos even, although this will be a bit tricky. But if you want to have exactly this patch with the image part, then you can download it from my Patreon, the link will be in the description. So I'm sure this is going to be a funny ride. And without any further ado, let's jump straight into it. Alright, so here we have our Max path, here we have Visual Studio Code, which we'll use for the shaders. So first thing first, we need a JIT world, right? To render our whole stuff. Let's call it main, let's give it full scale anti-aliasing, let's give it a default size. Let's give it enable by default. And one option that I want to give it as well is ortho 2, because we don't need the third dimension, we're going to work in 2D. Oh, I forgot to set floating. As you can see, my window just disappeared behind the Max patch. So that's it, floating. And cool, let's then create the GGL mesh. I guess that's the second thing we need. So it draws to main, let's give it as a color white. Then let's say draw mode points. Right. So maybe first let's start with the shader for rendering the GGL mesh, okay? Because we need to render circles from each vertex in the GGL mesh. So what we want to do with this shader is to take the vertices of the GGL mesh, which are just points, right? And draw a circle instead of a single vertex. And the shader to do that, the shader to get an input geometry and transform it into another output geometry is the geometry shader. So we're going to use the geometry shader to do exactly that. So let's first create just a JIT noise, 3 planes, float 32. Let's give it, let's say like 100 of those. Let's maybe say 101, which should be the same actually. And let's map the output from 0 to 1. We map it to -1 to 1, so the points will cover the whole surface of the rendering window. Let's actually set the erase color to black, so the background color to black. JIT noise, JIT map goes into the vertex input of GGL mesh, so let's give it a look. And here we have our vertices represented as points. The points are really small, so let's make them bigger just for the moment, just to visualize them a bit better. So there they are. Cool. So let's now create a GGL shader. This GGL shader draws to main. Let's give it a name. It's going to be circle packing render.jxs. And oh, that's actually the file name, so let's actually say file. This is going to be our file name, and the name is going to be exactly the same apart for the JXS part, because it's not file, right? We don't need an extension. So circle packing render. Now this file doesn't exist, so let's double click on it. Let's say save as. I'm going to save it on my desktop as circle packing render.jxs, as we wrote in the shader. So if I double click on it now, it will open the shader on Visual Studio Code. So this is the shader we're going to use to transform the dots into circles. Now what we want to do is we don't want to use the model view projection matrix. we want to use the model view matrix because we want to work with camera coordinates. So, okay, let's see. This is our 3D world, and is our vertex. When we transform this vertex with a model view projection matrix, what happens is that this vertex gets placed in a 2D position on the rendering window. So it loses completely its three-dimensionality, just becomes that position on a 2D screen. But we don't want to work with position in 2D screen, we want to work with this 3D position, or 2D position, but in the 3D world. So what we want to do is to transform it into camera coordinates. So if you remember, I explained this in another video of mine, but I'm going to explain it again. So normally the center of our coordinates is at the center of the 3D world. But if we transform this vertex into camera coordinates, then the camera position, which is our point of view from which we observe the scene, right? This becomes the new 0, 0, 0. And we want to work with this set of coordinates. So this will be then the world will start then from the camera. So we want to work with this set of coordinates because we cannot work with just the vertex coordinates, because the vertex coordinates will be relative to the actual object. So if I have a cube here, its vertex coordinate will make it that the center of the world is actually the center of the cube, but we don't want that. We could work with world coordinates, so just using the center of the world as the 0, 0, 0. But this is a bit more complex. We don't have the matrices available right away in glsl. So the easiest thing is to just work in camera coordinates. So transform this vertex with a model view matrix, which will give us this vertex into camera coordinates. Okay, hope this is clear. If it's not clear, I will put a link to an old tutorial of mine, an old article of mine in which I explain exactly that. So let's move on. And let's say model view projection matrix, model view matrix is the state model view matrix. So we take away the projection part. Then we also need another matrix, which is the projection matrix, because in the end we actually want to have this vertex into this 2D position in the rendering windows, so we need also the projection matrix as well. So this is as well type mat4, and state is going to be projection matrix, all caps lock. And then we want to bind it. So here is going to be the model view matrix, and then we create another bind param, and it's going to be the projection matrix to the program. Actually, we don't want to bind this to the vertex program, we want to bind it to the geometry program. So if you see this geometry program is called GP, and this is where we want to bind it as well, the model view matrix. So both these matrices, we want to bind them to the GP program. Right, let's make a bit of order here. We can change the description. This is not the default shader, but this is the circle packing rendering shader. Right. Name, we can change it as well to circle packing, not parking, shader, render shader. Cool. So we got the position, we got the color as well, which we will actually use later. Just want to put them under the position because these are kind of the buffers of the GGL mesh, and these are uniforms that are the same for each vertex, but the buffer is going to contain different data for each vertex of the GGL mesh. So in the vertex program, we actually don't need the model view projection matrix. Oh, you know what? I think I made a mistake. Actually, we want to have the model view matrix in the vertex program because we transform the vertices in the vertex shader and send them in camera coordinates to the geometry shader. So this is going to be the model view matrix that we're going to use here, position and color. We can send out the color, that's all good. So here we want to transform the GL position not using the projection, but using the model view matrix. And GTout color is going to be color, good. Now here in the geometry program, actually we don't need all this part. We just need the name of the program, which is GP, and the type, which is geometry. And then we want to say it here that we don't have, as input, we don't have lines. Remember, this is the default shader, right? So it's all set in the wrong way for our purposes. We want to have points as input, and we want to have line strip as output. Max vertices, we want to have 100 vertices. So why line strip? Our circles is not like a continuous line, right? It's a set of lines that when connected together, they create a circle. So when all the vertices are connected one after the other by lines, this is called a line strip. So our output type is going to be line strip. There is a bunch of output types. You can check them on the glsl reference language website or book. So line strip is all we need. And then max vertices is the maximum amount of vertices that we can output from the geometry shader. Now, for each vertex that comes in, this means we can output maximum 100 vertices out. So that's the more vertices we have, the more smooth is going to be the circle. Because if we just have like 8 vertices, this is going to look like an hexagon or something. While if we have 100 of vertices, so we have 100 lines, this is going to look much smoother. So that's the purpose of that. Let's go on. Inside here, we want to get rid of that because we're actually going to create a for loop. Because we want to add all these vertices. So to do that, we're not going to add them manually. We're going to create a for loop. So I is going to be less than 100. Let's actually do like this. Let's define our maximum amount of vertices as a preprocessor statement, I think it's called. So basically we set a define, and this is like declaring a variable. It's just a fancy way to declare a variable, and then we can use it in our code, and this will always represent the number 100. So I is less than the max vertices, because then if we want to change how much the maximum amount of vertices, we can just change it by change this variable, and this will be applied in all our code. So then I plus plus. Right, so we want to put this part of code inside our for loop, because this is where we are actually adding a vertex to our to the pipeline and sending it down to the fragment shader, and then at the end we can say and the primitive. So the primitive will be all the line strips attached together. So there was a 2 here because it had as input, it had like triangle or something. So for each primitive that comes in, we can access the position of all the vertices that compose the primitive, like the triangle. In this case, the primitive is a point, so there is only one vertex. So the index in this array is going to be 0. So what we want to do is to use the sine and cosine to create the points around our vertex. So if I take the cosine of a number, for example of 0, this is going to give me the number 1. And then if this number increases, then if I take the cosine as the x component and the sine as the y component, that I will have, then I will have a circle. And then I just have to sum the coordinates of this circle to the position, so the circle will always kind of move around that position of our vertex. So that's the plan. So let's create the x component. This is going to be equal to the cosine of an angle multiplied by a radius. Now we don't have a radius. Let's create a float, call it radius, give it a value like 0.1. We are going to modify this later, but that's how it's going. That's just for the moment to see if the stuff is actually working. And the y is going to be the sine of that angle multiplied by the radius. And then what we want to do is to sum to GL position a vector 4, because GL position is actually a vector 4, with x, y, 0 for the zeta, and 0 for the 0 for the fourth component, because the fourth component is used by the pipeline to do a bunch of calculations. We don't want to mess with that, so we just sum the number 0 to that. And cool, now we just need an angle, so our angle is going to be I divided by max vertices. So this is going to be from 0 to 1, Actually, this should be max vertices -1 if we want, because I will maximum be max vertices -1. So if we divide it by max vertices -1, this will go from 0 to 1. And then we have to multiply this by 2 pi. So what is 2 pi? And after a very fast Google search, I discovered that 2 pi is exactly that number. So we multiply this by 2 pi, so we will have the full circle. Now, we probably got a bunch of errors. Not yet, because we actually didn't assign the shader to the mesh. So let's do it now. Let's say shader. Shader, this is called circle packing render. Did I write it correct? Yeah. So let's assign the vertices here. And it doesn't give us error, but also doesn't work. Let's connect here a GTF FPS GUI just to see if stuff is actually being rendered. Cool. It's not giving us error, so we didn't do anything wrong, but it's just doing the wrong thing. It's just rendering the points in the wrong way. So let's go down there. Let's see if we forgot something. Right, we forgot to transform those vertices with the projection matrix to have them into the rendering window, into the coordinates. You remember we wanted to do that. So let's go here. Let's create this uniform. This is a mat4. It's called projection matrix. So once we have that, we want to multiply the projection matrix by this position. We can also send it to the next line just to have a bit more space. And let's see now, this should theoretically work. Doesn't seem to be working though. Oh, and you know why it's not working? This is a bit tricky because I is actually an integer. So if we divide this by another integer, this will just give us 0 the whole time. So what we need to do is to cast y to a float. Let's see if this does the trick. Yeah, this does the trick. Okay, this took me quite a while to find out because this is pretty tricky. Okay, cool. So this is now working. We got the vertices represented as circles. Pretty funky. All right, let's go on and create our transfer feedback system. This will be where we have the actual algorithm to check if the circles are overlapping with each other. Okay, so let's create a ggltf object. We're going to need a couple of inputs. And let's give it a shader file, which we will call the circle packing tf. Not a file, sorry, shader name. So let's then create another ggl shader, which we will give it as a name, circle packing underscore tf, and the file is going to be called circle packing tf.jxs. Right, without too much fantasy. Cool, this file doesn't exist yet, so let's open that. The second shader, let's go into file, save as. So that patch is in the desktop, so I'm just going to save it into the desktop. Circle packing tf.jxs. Cool. And now if I double click here a couple of times, you should then open it inside Visual Studio Code. Right. So this is again the default shader, which is definitely unfit to work as our transfer feedback shader. So before we do the modification on the shaders though, let's create our buffers. So ggl buffer, this is going to be of type position, and the out name that we're going to give it is going to be out position. If you don't know anything about the transfer feedback and what I'm doing right now, I have definitely 2 to 3 videos, 4 videos, definitely a lot of videos about how transfer feedback works. So you may want to review those first before, if you're not getting what's going on. I will leave links into the descriptions. Maybe they will even pop up to some side of the screen right now, or maybe not. Let's see. Anyway, you will find them in the description. So one was going to be the position, and the other we will use the normal buffer. So the buffer that normally will contain the normal values for the vertices of the mesh, but we will use that for the growth, right? For the growth of the circles. So we're just going to call it growth, the output name, and then we connect these to the GGL mesh. Now, this noise matrix doesn't go anymore inside the mesh. Now this is going to be our position, so we can fill the position buffer with that values. So let's see if this is working okay. This is at least working. Awesome. If we try to enable the transfer feedback, let's actually create a message. It will definitely give us an error because the shader is completely unfit to be used with the transfer feedback. So yeah. Plus, we should also fill this other buffer with some data. So let's actually do that. Let's simply create an empty matrix, which we will bang inside this buffer. It will just fill the buffer with zeros, but this is important to do because we always need to fill those buffer with some data. Doesn't matter if it's all zeros, they need to be filled somehow. So cool, let's now go inside our shader, the shader, the circle packing TF shader, and let's make it modified so that we can use it with the transfer feedback. So let's delete this color and model view projection matrix. These we definitely don't need. Let's delete this here. Let's delete this here. We don't need a JIT out per vertex. We don't need a lot of stuff actually. We don't need the whole geometry program. We don't need much of the fragment shader as well. We can just delete everything apart from the version and the main function. Maybe we can even delete the version, not sure about that. Just leave it like that. And okay, now looks good. So let's create the second, the position input, we will call it I position, so I as in input. And the other will be I growth, which uses as a state the normal buffer. The normal is as well a vector 3 because it has 3 components, x, y, and z. So that's all good. So let's now bind it. We call this I position. Let's bind it, the growth. So I growth, we bind it to program VP. That's the only program we use in a transfer feedback. Oh, we could also use a geometry program, but we don't have it. We only use the vertex program. So input vec 3, this is I position, and then input vec 3, this is I growth. And then we just need to assign, just to check that everything works, let's just assign the I position, sorry, the O position to I position, and then O growth, let's say equal to, I growth. Actually forgot to declare those outputs. So output vec 3, we need to declare it as well, right? So O growth, output vec 3 O position, right? And okay, so now this should work. If we try to enable the transfer feedback now, right, we should not get any errors. Just to be sure that this is working, I always like to just sum this to something, just to check if the position, for example, just to check if the actual transfer feedback is working. It seems to be working. We are moving the vertices 0.001 unit to the right at each frame. Great, that was it. Cool, so let's now see how we can actually grow the circles. We will grow them like this. Let's add actually to the O growth a vector. So this will make the O growth increase at each frame, right? And the cool thing is that we can access this buffer in our render shader. So if I open now the render shader, we can create this buffer, the normal buffer. Let's call it I growth as well here, the state normal. So this is the same buffer that we are writing into from the transfer feed mesh shader. We can access it in the actual rendering shader of the mesh, the shader attached to the mesh. So let's go here, let's bind it. We call it iGrout. Program is the vertex program, I think, right? Yeah. So let's put an input here, vec3 iGrout, grout, and let's pass it to the geometry program from our Jitter vertex structure. So this is going to be called radius. This is the radius of our circle, right? So let's write into it jit out.radius equal to iGrout.x. So only the first component. Remember, in the transfer feedback shader, we are only summing something to the x component of this vector. So in the so here we're just switching the x component for the radius. Now in the structure, the input structure of the geometry program, we can write radius. This flat here means that this is not going to be interpolated between the two programs from the vertex to the geometry. Now, from the vertex to the geometry, there is anyway no interpolation. Mostly the interpolation happens from the vertex to the fragment or from the geometry to the fragment. So, and this interpolation happens automatically. But anyway, I just write this flat thing doesn't hurt. We could also not put it. It doesn't change anything, I believe. So now here, instead of using the radius as a variable that we declare ourselves, we can just say jit in 0, because every input into the geometry program is actually an array. You can see this is an array. So since we only have one vertex, because it's a point primitive, this is always going to be 0. Is my mic actually good position? I hope so. Right. And then we can say radius. And we just copy that. We paste it here. Cool. So let's see. As you can see, it works. The circles are getting bigger and bigger because we are increasing the radius at each frame. Awesome. We are a very good point. Let's clean the window here. Let's go back into the transfer feedback and let's create our algorithm. So let's do like this. If the circle can still grow, and we will say, let's create a variable. It's going to be an integer. No, it's going to be a float. And let's call it can grow. And let's set it to 1, right? Now let's set it to, now let's actually call it should stop growing. Okay, and let's set it to 0. So 0 means false. So we can say no, it still should grow. It should not stop growing. So we actually don't set it equal to 0. We set it equal to iGrout.z, for example. Right? So we just use the third component of iGrout to set this value. And then when we write to oGrout, we should just grout, we will just use for the zeta value, instead of 0, we will just set this value, should stop growing. So if it doesn't change in the shader, it will always be the same value. So it starts as a 0 because this buffer is going to be filled with zeros. And so if this was at 0 in the first place, it will still remain at 0. But then we will say if should stop. So if it shouldn't stop growing, then so if this is false, or actually let's say if this is, let's make it explicit, if this is equal to 0, so it should actually grow, then we can say if it should grow, then we can, let's actually create a variable and call it increase, and let's give it a default value of something small, something like that. And then let's say, no, let's actually set it to 0, right? Let's set it to 0. And then let's say increase is equal to a small value. And then what we want to do is to loop over all the circles in the buffer, so all the vertices of the mesh, see what is their radius. So let's make a little drawing. So this is our circle, and these are the other circles. If the distance between those two circles, or whatever circle, is smaller than the two radiuses of these circles, so it means that they actually, if this distance is smaller than the two radiuses, this means that they're actually overlapping, and this we don't want, so we will say, okay, then just stop growing, and we will just set here increase. So if increase stays 0, then we'll just sum to 0. So that's the plan. So let's loop over all the... So in order to loop on all the other vertices of the mesh, we need to make this buffer... We need to make this buffer text buff, which means we can then access it as a texture from within the shader. And also the growth buffer, we need to make it a text buff. So text buff 1, that's the attribute. So from within the shader, we now need to declare those two buffers as new parameters, so as textures basically. And we will call it text position. And this is a texture, so it's going to be of type int. The default is going to be 0 because it's the first texture that we have. And now let's actually copy that. And this is going to be the text growth. And the index of that is going to be 1 because it's our second texture that we attach to the GGL transform feedback. And then we actually need to bind them. So I will just copy that and say text position, and here I'm just going to say text growth, right? That's good. Inside here, these are basically uniforms, so this is going to be a uniform, and it's called sample buffer the type, and this is called text position. Let's copy that and call it text growth. Cool. So now we can access this inside the shader. So let's create here a for loop inside our if statement. Let's say I equal to 0. I is less than the size of our matrix, which at the moment is 100. So maybe we should also create a variable for that. So int num circles or something. We're not using a define here because we may want to change that. If we change the size of the matrix, we may want to change that with a parameter, so we cannot use a define statement. And let's say I++. So let's actually just replace this 100 with num circles. Cool. So if I is different than the built-in variable GL vertex ID, the GL vertex ID. Okay, so GL vertex ID represent the index of this vertex, basically. So this means if this is not, if I is different from the index of this vertex, so it means we are not comparing this vertex with themselves, then let's create a vector 3, and let's say this is the other position, so the position of the other circles. The other circle that we are sampling. So we can use, to sample a sampler buffer, we can use this glsl fetch function, which works with only with the 1D textures, and a buffer is always a 1D texture, basically. So the name of the texture in this case is going to be text position, and the sampling is just an integer, it's going to be I. So we will compare the position of this vertex with the other position, and then we need a float with this, which is other radius. And this is going to be again glsl fetch, text growth, and then I as well. Cool. So then let's create a float, and this is going to be the distance between the two circles. And there is a function in glsl 3 which is called distance. So we can say the distance between I position, which is the position of this circle, and other position, which is the position of the other circles. And then we can say if dist is smaller or the same as this radius, which is basically iGrowth.x. Let's actually create it as a variable. So float this radius, it's going to be equal to iGrowth.x. So if this is less than this radius plus the other, radius. It means we are actually, these circles are actually overlapping. Then we can say that igrowth.z, now it we say should stop growing, right? Should stop growing is equal to 1, so it actually should stop growing. And then we break this loop. And this should be it. Okay, let's see if we're getting any errors first of all. Yeah, of course we are. User one declare identifier order position. Why is this then undeclared? Incompatible type initialization and no available conversion. Of course, because a texture is always a vector force. So in this case, we need to switch x, y, x, y, and z. And for the radius, we only need to switch the x, the first component, right? That's pretty clear, actually. So let's see. Okay, they start growing. They overlap. This algorithm is not working at all. Okay, cool. So let's see what's the problem. Okay, you know what was the problem? That I had to write I position x, y and other position x, y, otherwise it will not work. Now I don't understand exactly why this is the case. It just looks like in this way it will actually work. Oh, did I write something wrong? Yeah, I put a comma instead of a dot. So now it should work. Right, let's make them grow a bit faster. Let's actually create a parameter for the growth. So param name, this is going to be growth speed. Let's actually call it u growth speed, like because it's a uniform. Type, it's going to be a float. Default, it's going to be something like 00001. And then let's bind it. So u growth speed, and then here let's create another uniform. This is going to be a float, we say u growth speed, and then let's use it instead of our increase value here, right? So let's start from scratch. Okay, cool. Now we can, as you can see, the algorithm is working. Sorry, I didn't show you before, but it's actually working. So let's create a prepend message param. So this is going to the circle TF here. Let's make a bit of space. And let's prepend u growth speed. So that's it. Start again, make this faster. Okay. Okay, this was a bit too fast. You can see that if the growth is too fast, then they will actually overlap. Actually, I think we should say if the distance is smaller than the radius plus the other radius plus this increase. Actually, this could be optimized. So we should say this radius plus other radius plus increase, because we are also increasing the radius in this frame. We're also increasing the radius in this frame, so this should be accounted for. But actually we could do something like that this radius plus equal to u growth speed, right? And then this we use it as, instead of increase here, we just say this radius, right? This makes sense. Cool, so let's see if this now, no, this is not working. Oh, of course, because I don't have to say plus, then I just have to say equal to. Okay, this was pretty much a mistake. I don't have to say plus, I grow plus that. This will just writing completely I growth from scratch. So using this radius and should stop growing. So let's see if now this works. And yes, it works, and it seems like it is a bit better, although sometimes they are still overlapping. If the growth value is too fast, because basically in one single frame they will grow too much to be below the threshold, so they will then overlap. Let's try with more. Let's try with the 500. So we just need to modify the size of these two matrices, and then inside here, our number of circles, we set it to 500, and then we're good to go. Growth speed, nice. It's working. So this was it. As I said, I will not go into the details on how to make the image effect. If you would like to check out this is done, I explain kind of the same process in some tutorials of mine already, but if you just want to get the patch, you can get it from my Patreon and support the channel. That will be, of course, very much appreciated. I got already 500 people supporting the channel, which is completely bonkers. I'm super grateful for all the support. It's really amazing. I could not do all these tutorials if it will not be for my patrons. Anyway, if you find this useful, a like and subscribe to the channel. This would be so much appreciated as well. And if you have any questions, let me know in the comments or on Discord, on Patreon. And I hope to see you in the next video. Have fun. See you soon. Ciao.